all over the world. It fell in Murchison, Australia in 1969. And what makes it so special is that so much of it has been recovered, over 100 kilograms. It was an observed fall, and so it was very important, and pieces were picked up and collected and stored properly. So there was very little terrestrial contamination with this. Murchison is a carbonaceous chondrite with a pretty high amount of water in it. And as we know, it is just chock full of organic molecules. Jamie showed us this data the other day, but I like to show it as well. So why is this one so special? Because it's just full of things. A lot of different classifications of organic compounds, carboxylic acids, amino acids, polyaromatic hydrocarbons. The vast majority of the organic material in Murchison is insoluble organic material, but even with that, they've been able to isolate and identify a very large number of molecules. As was mentioned yesterday, probably over 1 million discrete organic molecules have been isolated. And also talked about yesterday was the stereochemical importance of this. But what I'm going to be talking about are some of these sugar-related compounds. So similar to what Yoshihiro was talking about yesterday. And what Nicole and I have been really interested in is what's responsible for this rich array of molecules in Murchison. What are some of the formation mechanisms that could have formed these molecules? And how could they have survived upon delivery to an Earth? And so what we have decided to focus on is looking at how the shock of the impact affects reactivity and survivability of glycolaldehyde and dihydroxyacetone. As was mentioned, these are not molecules that have been found specifically in Murchison, but have been found quite a bit in the interstellar medium. What I'm going to talk about today is going to be glycolaldehyde in particular, this 2-carbon sugar, in part for a lot of the reasons that Yoshihiro brought up yesterday. Larger sugars tend to be very difficult to analyze chromatographically. And so we have a more complete story for this smaller glycolaldehyde. And so what we were interested in doing is modeling some of these impacts. And so we went down to the Johnson Space Center in Houston to do the experiments to mimic some of these impacts. And we use their flat plate accelerator. So why specifically glycolaldehyde? As I said, it's not explicitly been found in Murchison because it is a fairly highly reactive molecule. It has been detected quite often in the interstellar medium, in Sagittarius here. And there's a fairly good idea about the mechanism of formation of this molecule, usually through polymerization of formaldehyde. However, there have been some recent in situ detections on several comets, including this is Hale-Bopp right here. And so we kind of took this as inspiration for our experiments. And in our experiments, we were looking at both neat samples of glycolaldehyde, but also samples stabilized with montmorillonite clays. Why the montmorillonite clays? A variety of reasons. They're known to be prebiotically relevant, suggested to be on an early Earth, and they're also very similar to minerals that have been found in comets. It's known that some of these clays are catalytically active, and so we thought that these would be a good model for some of our experiments. Okay, so here are some nice pictures from our time at Johnson using their flat plate accelerator over here on the left. It is just a trick of the photograph here that it looks curved. It is actually a straight gun right here. Here's the flyer plate. So as it goes from the right, our target is on the left, and so the impactor is this flat plate on the left-hand side. Here are some pictures of our samples before and after impact, and then our undergraduate student who went down one time to do these experiments with us. And so you can see it's a nice big metal target right here. This is the sample neat in the center, and then the sample mixed with the clays over on the right-hand side. So this top picture is the unimpacted sample. The sample in the middle is the one after impact, after most of the target has been milled off the top of it. And you can see that there's definitely some changes here, some darkening of the surface. When we scratch the surface here, what we can see is that most of the reactivity and most of the reactions we think are taking place right at the surface of this sample. Okay. So when we did this experiment, we've done several shots, but these are the ones I'm going to talk about today. So we did several samples, both neat, so just the glycolaldehyde on its own, but then also mixed with this montmorillonite clays. The pressures that we looked at ranged from 4.5 up to a highest pressure of about 25 gigapascals. Okay. So when we did these experiments, we were expecting a variety of reactions. And so we had some targets that we were definitely interested in looking at. So we were interested in trying to identify some decomposition reactions. So taking our glycolaldehyde and either cleaving it down to single carbon or doing some reduction or even oxidation chemistry here. And then we were also kind of hoping for some dimerization reactions, but mostly what we were predicting were our decomposition reactions. So this work was published several years ago at OLEP. And so what we were very excited to see, we got a lot of reactions to actually happen when we were doing these experiments. I'm only presenting the results from the GLA and clay results. Mostly what happened with the pure glycolaldehyde when we did these reactions is just straight decomposition. We really didn't see too much reactivity. Most of what we got out was just kind of a black goo. And so the really interesting chemistry took place when we had the stabilization with these mineral matrices. And so what we can see, these are relative amounts relative to an internal standard. And so what we can see is that we got survivability of the glycolaldehyde at all pressures. And we also saw significant amounts of reactivity here. Really exciting for us is we saw significant amounts of dimerization in our reactions. We saw samples of threose and erythrose being formed, and some interesting stereochemical results here that I'm just not going to talk about today. We saw a few of the decomposition reactions, including glycolaldehyde and ethylene glycol. Probably the production of these were coupled to each other. But why does this all matter? Who cares about this anymore? Well, about the same time that this paper came out, there were a lot of reports in the literature about comets and in situ detection of comets. And so there were at least 5 and maybe more at this point detections of comets, of glycolaldehyde on comets. And so what we've done in our most recent paper is we took these comets, we took all of these detections of the reported detections of the comets, kind of estimated some masses of glycolaldehyde, ethylene glycol, and water that might be present based on the reported mole percentage of glycolaldehyde relative to water and ethylene glycol relative to water. And so these are in billions of kilograms. And so what we see is that these comets could have been really rich sources of organic molecules, in particular, these very reactive starting materials, glycolaldehyde and ethylene glycol. Well, it doesn't help us too much if they stay out in space. And so what we then did was we took these reactivity, we took our yield reactions that we had from our previous paper, and we applied them to the amounts of glycolaldehyde that could have been present in these comets. And what we can see is that if we make some assumptions of the impact pressures, our low end and our high end impact pressures, and we can see that the amount of glycolaldehyde that could have survived in an impact is really, really high for each of these individual comets. And in addition, we can see that we also were able to form significant amounts of these, very simple sugars and other biologically relevant molecules. That doesn't help us too much. We have detections of a few comets. And so if we extrapolate this to the cometary flux of the first billion years of the Earth's history, again, we can see that, thinking about, as Stephen said, contaminating the early Earth with our organic molecules, we can see that we could have delivered quite a large amount of reactive organic carbon to the surface of the Earth. So where did it all go? You might be thinking we are not up to our earballs in glycolaldehyde at this point. Well, glycolaldehyde is a very important part of the foremost reaction. And so this could have been incorporated into the foremost reaction to help produce some of the simple sugars and biologically relevant materials here. In the last couple of minutes, I just want to talk briefly about some of the current work that we're doing. If you go into the literature and you look at these types of experiments and other similar reactions, other similar studies, what you see is that for the most part, there's not a lot of work that's been done on sugars. And, you know, as was mentioned yesterday, they're very difficult to analyze. Lots of different conformers in solution. And so a lot more work has been done on amino acids. And so what we've started doing is also incorporating some amino acids into our studies and looking at these. And so similar to some work that Jamie has been doing, what we've started doing is going into the literature and looking at all of the amino acids that have been detected and conclusively identified in the meteorites, and started looking at some of the structural classifications. Here are just a few that we picked out: linear versus nonlinear side chains. And then we also have some other structural classifications that we've been looking at as well. We've been taking all of this data and looking at the composition of the amino acids as a function of meteorite class. And so what we can see is that the different meteorite classes which are shown in the different colors on this bar graph, is that we're seeing fairly different amounts of these different structural types of amino acid per meteorite class. So again, this is our linear versus branched side chain data, and we can see that there are some definite trends. And so this has some pretty interesting implications for maybe formation mechanisms and other things. We've compared this data to some impact experiments that have been published, and the linear versus branch side chain data is shown right here. And so what this graph is showing is kind of looking at the survivability of amino acids based on structural class. And what we see is that other structural classes, yes, I see the time. This is my last slide and then my acknowledgements. The linear amino acids tend to have a little bit lower survivability than some of these other structural classes. And so this is some really interesting and exciting data that we have. We're currently working on a manuscript, hopefully have this out by the end of the year. So this is kind of some of the other stuff that we've been working on. As I said, this is my last slide. Thank you so much for your attention. These are the students. These are all undergraduate students who did all of the work that I presented today. Nicole Zellner, of course, is my collaborator extraordinaire, and then the funding. And thank you for your time and attention.